Afternoon, everybody. In the absence of somebody chairing, we might as well get going, given that we're pretty much on time. Good afternoon. My name's David. I'm a developer and part-time, sometimes scientist, depends what day it is, working with the Bureau of Meteorology at head office in Melbourne. Today I'm going to walk you through a couple of the systems that we have that generate water forecasts. So we're one segment of the Bureau. A lot of you are probably very familiar with a lot of our weather forecasts and sort of flood warning and those sorts of things. The stuff I'm talking about today is possibly an aspect of our work that you may not be that familiar with. I'm going to say up front that this presentation might be slightly different to some of the others you've seen at the conference this weekend. I'm not going to get hugely technical. I think a lot of what we're doing is showcasing how important Python has been to us in getting our work done, and some of the really cool things that we find in Python and what it does for us. So I'm going to go through sort of four things. I'm going to give you a brief demo of two of the systems that we've got. So I'm going to switch across to the web and try live demoing from the web, assuming our internet connection doesn't let us down. Show you a couple of our products. Then I'm going to walk you through who we are, what we do, give you an idea of why we're doing it. I'm going to give a bit more detail on the two products that I've shown you and the systems that underlie those products, so the actual Python components of it. And then I'm going to go through a couple of examples of some of the really nifty things that we've been doing with Python that may not be news to some of you, but might be news to other people. We might be able to share some new things with you. So I'm going to switch out to a browser. I suspect a lot of you, particularly if you're local Australians from somewhere, but if you're from overseas, you may not have seen Bureau's main website. So this is the main landing page on the Bureau of Meteorology website. Our section is primarily involved in water forecasting, so there's the water information link down the bottom here, which then takes you to a somewhat older styled page here. And there are two products that I'm going to walk you through today, the seasonal streamflow forecasting system and the hydrological reference stations. So the first I'm going to touch on are the streamflow forecasts. This is a service providing 3-month outlook streamflow forecasts, and they're updated every month. So basically we give an idea of the amount of water you're going to have flowing down any particular river in the places that we service, with an idea of whether you're going to have low flows, median to normal flows, or high flows. And so for each of those sites, we generate a whole bunch of products which we can then provide to our users. Those of you who are very familiar with Matplotlib may notice the look and style of these plots. They're all generated through Matplotlib, through the modelling system that we've got that we use internally. And all of that's just presented through a very simple web front end. So we've got a whole lot of different graphical products of varying complexities for different audiences, effectively, as well as a whole lot of other data products. The actual data can be downloaded. There's table formats for all the products in order to meet accessibility requirements and those sorts of things. So that's just a very quick overview of our seasonal streamflow service. The second product I'm going to touch on is the Hydrological Reference Stations portal. This is a product that gives historical information for 221 sites across the country. So once again, these are all river monitoring sites. So showing the historical river flows that you've had at each of these sites. We've got a variety of different products again, and a lot of these are statistical-based products showing trends and step changes and all sorts of things. Once again, going through from very simple plots like this one through increasing complexity where you can add more detail to each of the plots, all through a JavaScript-driven front end. You've got different time series of different frequencies, so you've got annual data, seasonal data, monthly data, through to the daily data. The whole lot of statistical analysis done on each of those. So all of this analysis is done in Python. Okay, so who are we and what we're doing? A lot of people may be familiar with the Bureau, as I mentioned, through their weather role, but the water information role is a relatively new role for the Bureau. A 10-year program began in July 2007, and so we're about halfway through that program, developing a whole lot of new products to providing water information to the Australian community. So there's a lot of funding associated with that, and a lot of funding for research and development, and a lot of staff that are employed under this new program. Within the Bureau, I sit within the extended hydrological prediction section. So basically we have responsibility for water forecasting for anything that's not a flood. So anything of a longer time frame out to 10 days, monthly, seasonal, annual, decadal forecasting. We work in a unit that is a combination of developers on one hand and scientists on the other. So we have a group of hydrologists, and there are 2 of us who are professional software developers. In that environment, we find that Python is a perfect fit for us, that it allows us to move from scientific type programming where we need to meet with how scientists think, so to be able to develop software that's maintainable and that we can look after and put into operations within the Bureau's infrastructure. And we have a big role in transitioning that research, that scientific side of things, through to an operational service. We also have strong links with research with the CSRO through WRADA, the Water Information Research and Development Alliance, and the university sector. So we work with a broad range of people with very different backgrounds. So it comes and touches back on what Tennessee was talking about this morning about people from different domains needing to find common ground to be able to talk about things. Okay, so there are 2 systems I'm going to touch on. The first of those is the Wafari seasonal streamflow forecasting system. So we have this framework, this modelling framework that we call Wafari, which is a Python system, which generates the forecast that I briefly showed you before in the web portal. We deliver at the moment to 78 sites. That's growing constantly as we progress through time. We issue a forecast for the next 3 months total streamflow, and we update that every month. So all of that content's generated by Wafari. Underneath that, at the moment, there's a statistical component that does the actual forecasting based on a Bayesian approach developed by CSRO. And this has gradually been developing over the last few years, with forecasts first being released public in 2010. We're actually moving now away from the statistical approach and into a dynamic modelling approach, where we're actually modelling the hydrology itself directly. So at the moment, the system is all written in Python, but with a front end that makes it accessible for hydrologists to be able to experiment with the system. And we also get the ability to integrate within that system a whole lot of different hydrological models. So we've got our main framework, which does all of our data handling, all of our input and output, our product presentation, the graphical stuff, and then we've got a whole lot of different cores that fit inside that. And we need to provide the hydrologists who have self-taught sort of programming skills and some programming skill, provide them with facilities to be able to get in and play with the models and tweak configuration and change data and those sorts of things. And so the way we've got that do that is we use a shell, use IPython. Basically, we write all of our code and we provide little toolkit commands that we can expose via IPython, which gives us a really powerful framework for allowing those scientists to get in there and use the tools. So they can run a particular component, they can say, okay, go and grab me the data for this site, I want to have a look at that data, and they can plot that up. Or they can say, now they've got that data and I've checked that's okay, they can go off and run an actual model and see how a forecast looks using that observed data. They can change configuration options for each of the models and all those sorts of things. So it's a very powerful tool for them and for us. One of my colleagues added that little note at the bottom there that in terms of providing education and improving how we can communicate with the scientists, if we give them this sort of interface, they can become people who help develop the system as we move forward. Once we've got that, we can then tie everything together in workflows. So by providing interfaces to each of the tools, so with those tools, as I mentioned, data handling and graphic and product generation, we can then provide workflows that the hydrologists themselves can tweak as well. So we can just generate one list of commands, off it goes, and generate forecasts for all of our 100-odd different forecast sites that we're running in development at the moment. One of the really powerful things for us is the ability to really rapidly customise graphical products using Matplotlib. I've got a couple of examples on this slide. The top left there, we've got our main forecast product showing the likelihood of low, high or normal forecasts using just a pie chart. You've got more complex products using the actual probability distribution on the right. And then we've got a whole lot of products that show forecast skill and all sorts of things spatially and in terms of a tabulated plot like that on the top bottom right. And the ability to really get in and customise these things and then store that configuration and regenerate these products in Matplotlib is really powerful for us. So a couple of the challenges with this system. As I mentioned, we have to support all sorts of different models, and we're constantly increasing the number of models that we use. The plot on the right is a diagram one of my colleagues has put together that shows how we manage to do that. We keep all of our data handling and everything separate in different modules, all our verification in separate modules. We manage to package everything up nicely, and then we then interface directly with each of the models separately. A lot of the scientific code, the research code that comes out of CSIRO, it generally tends to be Fortran 90, or earlier versions of Fortran even, with bits of R and all sorts of other things in there. We don't have to rewrite a lot of that. We want to be able to use it directly. Python gives us that ability really, really easily and makes life quite straightforward for us. But then we need to be able to get that fine-grained control over input data and model configuration and those sorts of things, and also product generation. So just giving an example on how we get around that. At the moment, initially, subprocess was used just to call out the Fortran directly after dumping all of its output to file, but we're now using F2Py to directly compile in those Fortran modules. And then we can just set up common interfaces to all of our models. So it's just a code snippet example of how that interface works for us. We can initialize the model, set up its initial state, and then run the model with its input data. And we can then apply that to any of the different hydrological models that we're using. The other major challenge we have with this system is to do with data management. We need to acquire data from a variety of different sources. We need to get our input rainfall observations. We need to get input water level streamflow observations. We have forecast input data in terms of rainfall, all sorts of things that need to get into the system. We need to be able to manage that data, and we need to be able to make each of our forecasts replicable. So if we make a forecast today, we need to be able to go back and make that same forecast for the same point in time a year later with the same version of the software to ensure that we're not changing the system and changing the forecast retrospectively. So we use a few different approaches to make sure that we can do that, and a lot of that means that we need to be able to get the same input data to run the same forecast. So the way we do that, we have at the moment just a relational database that is the point of truth for all of our data, and then we synchronize from that database into a local file store. And that local file store we use to drive the actual system, so we can reduce the number of database queries we need as we run the system, which allows us also to run the system offline effectively. We use SQL Alchemy to access our databases, which gives us a really powerful interface to the database without having to write much code, which is great. And we use HDF5, which has been mentioned a couple of times in a scientific context today, and PyTables, which is a really, really nifty way to be able to access relational database type data in a local file. The image on the right there, you may not be able to see much detail on it, just shows the contents of an HDF5 file in a simple Windows or Linux-based GUI. It's actually Java-based, I think. You can see you've got a tree structure of each of the bits of data that you've got in the file, and then the actual data is stored in tables within that file. So you can get a really nice hierarchical data structure in there and store that and move it around and use it on whatever system you need. So moving on to the HRS. This is a different system that's much newer than the streamflow forecasting system. So it uses some slightly more recent versions of some tools, which is really nice for us to be able to move on a bit. We also have had a lot more flexibility in how we design the system. We don't have to rely on being able to integrate older code into it. So at the moment, we take in 221 time series. So they're just a simple time series for each site, and a whole lot of geospatial information, which we then process, dump out a whole lot of images, and a whole lot of configuration information, and a whole lot of that spatial information. That all gets dumped out to file and passed off to the web portal. So the web portal itself is all driven statically, and I'll get to why that is in a minute. So the main challenges we had here was integrating a lot of statistical analysis, which we had to test against existing code. The challenge being that a lot of that existing code were Excel spreadsheets that had been developed by the scientists themselves. So not only do we have to go and implement all these statistical tests and things, we had to try and get the same answers as had been derived previously in Excel. So there's a lot of testing code that we had to write, and using Python's unit test and those testing frameworks made that really straightforward. The other biggest challenge we've got with this is how we deliver the product. We have to be able to work within Bureau's enterprise infrastructure. which means that it's much harder for us to deploy apps using a dynamic server-side framework. So whilst it'd be nice to be able to deliver this content via Django or some other framework, getting that deployed in our infrastructure is a little bit harder. So at the moment we're using a static-based approach where everything is pre-generated and then provided with a dynamic client-side app to do all the interaction with the data. And we have to be able to update it. So that meant that we have two systems. We've got our front-end web app, and we've got a toolkit that generates all of the actual data that gets pushed out. And that's all written in Python. If you're in the session before this, you heard about pandas. And I'm probably going to mention a few of those things again. Pandas effectively is the core of this system. We're doing time series data handling, and Pandas does that in a really, really nice way for what we're doing. So we use it heavily, along with Matplotlib, of course, for all of our imaging and plotting, and also the GDAL Python bindings, or the OGR Python bindings to do all the geospatial work. A couple of things that we use really heavily that are really useful to us. First is, and I'll touch on this in the next slide, is keyword-driven arguments to Matplotlib. It's one of those little features of Python that can get quite ugly but can be really powerful at the same time. And then pandas with its time series handling stuff, being able to do the grouping and aggregation straight out of the box and being able to have multiple views on the same data set really simply. So getting a graphic out of it, getting an HTML table driven straight out of the data set and getting CSV. So the web portal then provides access to all that data. I'm not sure how much of that you'll be able to read, but this is just to try and illustrate how we've managed to derive all of our images. So there are, I think, 60-odd different image products that we provide through the HRS. And generally working with colleagues who have different views and people in management who have different views on how images should look and how they should fit with the corporate look and feel and all those sorts of things is one of those really time-consuming and really difficult processes you have to go through. And so it wasn't actually me that wrote this code, but one of our developers came up with a really nifty solution where we basically drive all of our image configuration through one central file that has all of the parameters to each of the plotting methods. And they're just stored as Python dictionaries. We need to pump them into the actual plotting methods directly. So all the colours, the x-axis, text sizes, and all that sort of stuff we can do in one place, not have to change and meddle with all of our code. So this method on the left is just pulling in one of those dictionaries, it's calling the params module, grabbing the daily time series configuration, and then passing off to our generic time series plotting method as those as keyword arguments, as parameters. It's a really useful little technique that we've managed to save a lot of time in revising how we present our image products, what colours they are and how thick the lines are and all those little things that as developers we may not care about, but other people certainly do. Okay, so there are two products that I just want to do a little bit of show and tell on and describe some of the things that are underneath them that we're using. One of my colleagues was keen that I include a laundry list of some of the packages that make our lives so much easier. So here's the laundry list. There are sort of the usual suspects there. Pandas I've mentioned, NumPy and SciPy, of course. PyDAP, I'm not sure how many people are familiar with OpenDAP, which is a data transfer protocol for allowing subsetting and deals with gridded data really nicely, which we use for some of the gridded data acquisition in a couple of our systems. NetCDF is a scientific file format, along with HDF, which is used widely in the scientific, particularly atmosphere, ocean, climate field. SQL Alchemy and the OGR bindings are both really useful. Dateutil, I think, is one of those little underrated packages that sits behind so many other things, but being able to add and subtract dates in a regular format is really useful. We do have some internal Django stuff and some Matplotlib drives most of our presentation stuff. Color Brewer for finding nice little colour schemes and plotting things quickly to make them look attractive. Usually then somebody higher up in the management chain comes and says, use these colours instead, but it gets you a starting point. We use a lot of Python. In particular, the couple of our hydrological models have actually been re-implemented from their original format. Some of them are in fairly archaic Fortran, have been re-implemented using Python, so we get that inner loop, decent speed out of Python. F2Py we use a lot, RPy2 we use to integrate a lot of existing code. And then the usual suspects in our development cycle. I'm just going to touch on, I think I've got 3 slides left on pieces of information, pieces of little Python code that I use every day or answer questions that I'm asked every day. The most common of these, or one of the top two, is can you do this with this time series? And as I said, pandas has been mentioned a lot in the last couple of days, but I think this is a nice little example of some of the things that pandas does for me that I love. I love the combination of relational database type operations on a time series data set, so being able to do the group by and aggregate type functions, along with the ability to do time series type operations, regularizing and interpolating time series data. So the top little example there is a group by method. In the HRS, we can't just aggregate to an annual calendar year. We aggregate to a water year, particularly if you've got a monsoonal location in the northern part of Australia where the wet season straddles January, December. You want to keep all of that as one year's worth of rainfall or stream flow. So we use what's called a hydrological year or a water year, where we start as the start of the year is the driest month of the year on climatology. And so being able to do those sorts of aggregations with pandas is really easy. I've got a little method there that determines if a particular month for a particular date falls in the current water year or the previous year. Then it's just that one little one-liner, the annual TS equals daily time series, grouped by the water year, and then aggregate using sum. So that one line of code can take my daily time series and give me a nice water year-based annual time series. The other thing I love about pandas is the frequency conversion, interpolation. Often water level instruments, so observation systems on rivers, will just do observations at whatever time is appropriate. Often they'll only report an observation when the water level has actually changed. So all of your time series data is irregular data that could come in at 15 minutes, and then you have one 2 minutes later, and then another one 2 days later. So regularising that data is a common operation that we have to do. Being able to, just in that one little snippet there, regularise the data to interpolate it to 1 minute data, and then interpolating that, so you fill in just a linear interpolation to get every minute, and then interpolating that to hourly, just takes that irregular data and gives me back hourly data, straight out of the box without having to muck around too much at all with the data. So those little things in pandas I really recommend to anybody who's doing time series data. And it doesn't need to be environment type data. It was built with financial data and that sort of thing in mind. This is probably my most common request. Somebody say, can you read this file and do this with it in this system? Generally the answer is yes, because Python has everything that we need. The ecosystem of scientific type data handling is quite mature. Read CSV from pandas was mentioned in the previous presentation. There's a little example at the bottom there of being able to take in an arbitrary format and get a pandas data frame back from it, which I find really useful. And the fact that we've got bindings for NetCDF, HDF5, and pretty much any major DB database application is really handy. And the fact that all of these things will come back to NumPy generally as a lingua franca, that I can generally assume that any interface to any data format will come back to one array of a known type that I can then pass into whatever analysis method I've got. I find that really valuable. The final one that I often get from one of my colleagues is, this new feature's been released in this package, can I use it to develop this on our system? Which is great for development, but we need to be able to guarantee that our production systems are always going to be running in the same environment. So one of my favourite tools at the moment is virtualenv, and being able to use that with pip freeze and pip install R just to replicate an existing environment. Which means that we can have a new version of pandas running for development stuff, but we're guaranteed that we're going to have the same interface and the same results in our older systems, our production systems. So summing all that up, why Python for our water availability forecasting systems? The flexibility is really important to us. The ability to go from Python as glue, which some people see it as just a replacement for shell scripting, but to then the much more powerful scripting and then full object-oriented development is really, really great. The low barrier to learning is one of the biggest benefits for us, working with scientists who may not have a formal programming background, for them to be able to pick up bits of scripts and be able to do whatever they like with them, but then be able to develop them properly for operational systems is really valuable. As I said, the extensive third library support, particularly the ecosystem that Ed was talking about just before for scientific computing is really, really important. And the fast turnaround, getting things done really quickly, and then worrying about optimization and having the options there to do that properly later. Thank you. Unsilence or questions? Yeah.
I was just wondering, although you said that you have to generate essentially a static site from the public one, are the actual underlying data sets also available to download, like if not an API?
Yes. So certainly for HRS, there are text-based downloads for all the products. You need to go through and grab each one individually, but it's on the to-do list to actually improve that access to be able to grab the whole data set in one go. And we do actually have some stakeholders in some of the water agencies who are using some of the forecast data to drive their decision support systems. So some of the water storage managers will, particularly the Murray-Darling Basin Authority, will pull in our forecasts and use it to decide where they're moving water around the system.
We just developed an application for local water monitoring for GovHack.
Yep. Improving access to that data is something we're really keen to do. So.
Really great talk, thank you.
Thanks.
I'd like to ask, what do you use to build and run the models? Do you use any other Python packages or software?
The Fortran-based stuff is all just derived from F2Py to actually build it, so I think there's some scones happening under the hood. A lot of the other code is really just built using Make to make sure that we've got everything up to date. Does that answer the question, or is that?
Have they implemented it in just a raw Python or something?
Oh, okay. Yep. We've got a whole variety, and that's one of the really important things for us to be able to support a whole variety. We've got some that are Fortran-based, so the actual models themselves are Fortran-based. We've got one that's an implementation in Python, and we've got, I think there's one that's very simple that is raw Python itself.
Have you had any problems with NumPy and time series data? Performance problems, that is? I've never been able to scale it to my data sets, but just wondering if you had any tricks to share in that regard.
I find that if you just do the intuitive things like looping over NumPy arrays, you end up with shocking performance. But if you realise you've got a bottleneck and you can go back and make sure that you're using the inbuilt vectorization type methods to do any iterative type work on the arrays, you can actually get reasonably good performance out of NumPy. It often just takes a bit of mucking around with using some of the apply methods and those sorts of things.
I'm interested in both the Bayesian statistical modeling that you've got as well as the hydraulic modeling. Is any of this available open source for me to look at it in case I want to adopt it to a country other than Australia?
Open source is something we aspire to. A lot of the models themselves aren't necessarily developed by us and can be accessed through different means. I'm pretty sure some of the Sacramento type things are openly and freely available, and some of the French-based models that we use are openly available. The system itself, or FARI itself, we're open to collaborating with people on that. So if you've got particular interests in different locations, then come and talk to us and we see what we can do.
And then can you also give us a sense of the size of data that you're dealing with? Because how big is the size of data that you model upon? Is it in gigabytes? Is it in terabytes?
So it's geographically the size of the...
Right, yeah.
The seasonal streamflow system, at the moment, we've geographically got coverage. It's still southeast focused of Australia, but we do have growing national coverage. So we've now got some Tasmanian sites. There are a lot of Queensland tropical sites. Southwest Western Australia and the Ord region in Australia we're moving towards. And there's a big push to make sure we're a genuinely national service.
Thanks for the talk, David. I've often or sometimes heard people talking a little bit disparagingly about Matplotlib, as in it's not a great plotting package compared to other ones. Do you have any kind of feeling on how Matplotlib compares to other options?
We haven't experimented that much with other things. I think the fact that Matplotlib can integrate with pretty much anything else, and that things like pandas and a lot of the other tools will use Matplotlib directly anyway. The fact you've got integration with basemap if you want to do spatial type information as well, I found really useful. I think if we were going to look at plotting things differently, we'd actually be moving away from where we are at the moment with static produced images to a dynamic approach, in which case we'd probably actually be unfortunately moving away from Python towards a JavaScript-based client-side dynamic plotting sort of approach anyway. So we haven't really investigated more. Most of our efforts have been more towards dynamic client website stuff.
Hi. I think one of the things you said is that some of the code's also written in R in different places. How do you call out to R code that you run? Does that go via Python, or how does that work?
We use RPy2 to access what we need to. So we can, using that, you basically we'll have R code written off in a separate script that we can then go and call the methods in that and then pull the results back into Python.
Any more questions? No? Well, please all join me in thanking David for his wonderful talk. And
Thank you very much.